Okay, I think that makes it past. People have stopped joining. Good evening, everybody. I was going to do a couple of brief parish notices before we start, and then introduce our main speaker for the evening. We have two speakers this evening. Karen is our main speaker, and Jordan will be doing a short presentation later on about the work he's done on his degree to fly a muon detector to space. Well, not quite to space, but certainly on a high altitude balloon. So we had some interesting results. Second, the next meeting will be Friday, the 1st of September. Dr. Ashimaya will be speaking about the square kilometre array. So if you're expecting a talk in July or August, you will be disappointed, unfortunately, but that will make more time for observing. One small thing, I wear two hats. I wear a UK Radio Astronomy Association hat, and we now have a stock of Cosmic Watch muon detectors for sale. If anybody would be interested, they're on our website. If you're UK based, just press the button to order if you're interested in purchasing one. I think Paul may have something briefly to say before we crack on with the main business.
Oh, yes, it follows on very briefly. The demand for muon detectors has been just fantastic. And we're selling a lot. They're all sold at cost and put together by volunteers. And if you're at all interested in helping with the production, then do contact me, and we can have a chat about that. We're trying to increase the rate of production now that we've overcome the semiconductor shortage issues that we had last year. But that's it. Thanks, Andrew.
Okay, so to our main event. Professor Karen Aplin is a physicist with expertise in innovative instrumentation. And I think instrumentation is very close to a lot of the things that we do. And there's a very practical strain in everybody on this forum. So seeing how it works at the cutting edge, both in space and atmospheric physics. Karen, the floor is yours.
Thank you. Let me share. That working?
Yeah.
Yes, it is.
Yeah, okay. I should add, I can't see the chat. So if there are, I don't mind taking questions as we go through if people prefer that, but I'll need to be interrupted. Or I don't know, maybe you prefer to do questions at the end, but yeah, I'm afraid I can't see it because I've got my screen in front of me.
Oh, okay. Karen, what I'll do is we'll take questions at the end and I'll read anything on the chat out. And if people are ignored, they usually pipe up anyway. Okay,
good. Well, thank you very much for inviting me today. I'm going to talk about planetary atmospheric electricity, which is, you'll hear more, but it's essentially about lightning in planetary atmospheres and also ionisation, which, as some of you may know, is caused by mainly cosmic rays. And yeah, I'd call myself a physicist, but I'm currently based in an engineering faculty at Bristol, which is interesting and useful in many ways, actually, as well. Okay, so what am I going to talk about? Got an intro, and then I'll talk about lightning. So the sort of focus is this kind of science background, and then sort of how would you measure that thing, I suppose. So whilst I do work in instrumentation, I'm not going to talk about my own instrumentation particularly, but I can probably bore you with it in the questions or later if you want. So yeah, and there's lightning, everyone knows about lightning. And there's also a whole part of atmospheric electricity, which is not to do with lightning, which is driven by cosmic rays that ionize atmospheres and make charges that are significant in different ways. And then these two things are joined up by planetary electric circuits, which is a global atmospheric electric circuit, which is combining current flows and generation from thunderstorms. And then I'll attempt to draw everything together at the end. I'm hopping around topics quite a lot in this talk and also planets. So I've got symbols in the corners, which is supposed to indicate what I'm talking about. So if you can't follow, I have a lightning symbol, the sort of non-thunderstorm stuff. I've got a cloud symbol, and I've got a battery symbol for the global circuits part. Right, so this sort of one slide summary of the entire talk is that there's lightning has been detected on quite a few planets already, these ones that are pictured. It may also exist on some other planets, particularly Venus and Mars, which I'll tell you more about later. And in addition to that, as I suggested, cosmic rays and other ionization processes release charge, which is essentially electricity in all atmospheres. So that means all atmospheres are electric. So if you want to kind of not pay attention to the rest of the talk, then that's the one slide summary, but I shall now go on to elaborate about this in more detail. So the sort of basis for the approach I take to this is that the laws of physics are the same everywhere, and that means the same underlying scientific principles underlie atmospheric electricity. And what does that mean? It means you can use terrestrial analogies to sort of understand and illustrate things that happen on other planets, because obviously it's much easier to see what's going on Earth. You can use the same instrumentation to measure atmospheric electricity wherever you are, more or less the same instrumentation. And you can also test space instruments on Earth with careful choice of environment. So if you want an atmosphere with low pressure, let's say a bit like Mars, then you can go to a high, you can use a balloon and go up to the stratosphere, and the pressures and temperatures aren't so different to Mars. This means you can get quite a long way without having to have a big space mission, which I'm sure you'll agree means progress is a bit, in between the big space missions, you can do other things, because otherwise you're just waiting years for things to happen. And also, I think bringing together different communities of researchers is an efficient way to make progress. When I started working on this topic, I did my PhD at the University of Reading, Department of Meteorology, and I made an instrument to measure ionization from cosmic rays in the atmosphere. At that time, well, I eventually found out that there was a whole bunch of people doing planetary work and making very similar instruments, but the planetary and terrestrial communities just didn't talk to each other at all. And I think things have improved a bit now, and people share expertise a bit more across that interdisciplinary divide. And that means you make more progress, especially, as I've said, when it's difficult and expensive to go to space, particularly planetary missions. I mean, we're seeing many more CubeSats and things now, but you're not seeing very many interplanetary missions, which are still very expensive. So lightning. So what is lightning? Well, it's a big spark. And on the Earth, lightning naturally is found in thunderclouds or in volcanic plumes. We know lightning's been around on Earth for a really long time, at least 250 million years. And that is because there's fossilized lightning in rocks that are that old. They're called fulgurites. And that they're on Arran, for example, there are some fulgurites in the rocks on Goatfell. I've not seen them, but I've seen pictures of them. People can date those rocks. We know about fulgurites because sometimes, well, lightning used to strike brickyards and stuff where there were big piles of sand, and it would make a fulgurite in the sand by fusing the sand. So it's very hot and it fuses the rock, basically makes a sort of channel that you can see. So that allows us to date how long lightning has been around, and it's pretty much the whole time the atmosphere has been around. In thunderclouds on Earth, you get a mixture of ice and water, and these mix together, and you get, when you have collisions between the different phases of water, then you have transfer of charge. And in a hugely oversimplified picture, and this bit on the right here, this blue part, ice crystals will hit Graupel, which is soft hail. Ice crystals are being positive, soft hail negative, and then the ice crystals kind of waft upwards in the turbulence, and the hail falls down, and that leads to separation of positive and negative charges, which eventually builds up a voltage, and when that gets to be big enough, it breaks down in lightning. And so what do you need for lightning? You need convection, which is sort of turbulence, rising air, mixing, which ultimately creates a thundercloud. And you need this process called charge separation, which I've just referred to, between the different phases of water, to build up a big enough voltage that leads to breakdown. And there are many different types of lightning. You can have it inside or between clouds. You can have it from clouds to ground. And there's also a different category of lightning, which is above the clouds, which goes upwards from the top of the clouds to the top of the atmosphere, which are called TLEs, transient luminous events, for example, sprites. And there are other types of TLE as well. Here are some pictures of lightning. So on the right, This shows two types of lightning at once. That is lightning inside clouds in a thunderstorm. And then on the top left here, we have a red sprite going upwards from the top of the thunderstorm. These are very diffuse and very high up, so you tend to have to be a long way away to see them. And this is a more top left, a more familiar sort of lightning, a video one of my friends took of lightning from one cloud to another into a cloud, and also from cloud to ground. A bit less common is volcanic lightning. This is the same sort of process. It's transfer of charge between particles essentially rubbing together, but it causes lightning in ash clouds. And you get, yeah, as you see, you get quite nice lightning in those clouds. And occasionally the clouds, the volcanic plumes can mix with normal clouds, if you like, and sort of enhance the charging, or even sometimes they mix with a thundercloud that's getting going, so you can get a very powerful lightning there. So lightning's all very pretty and fun, but why is it important? Well, of course, it's a hazard on Earth. It kills people still now. In space, it can cause problems for sort of interference, noise, electrostatic discharges. Dust gets charged and it sticks to solar cells. That means your spacecraft has less power. And clearly, if there are crewed missions, only so far people have only been to the moon, but they will go to Mars at some point. There will be a hazard from lightning to them. The chemistry from lightning is also important. So there's this famous experiment called the Miller and Urey experiment, which is in the 1950s, which is when Miller and Urey put some stuff in a tank that resembled the early Earth gases that were like the early Earth's atmosphere, and they zapped it with sparks. And after some time, I think it's about a year actually of regular zapping, it made amino acids inside the tank. So there's this argument, which is beloved by me and my colleagues for grant applications, to say that lightning could be involved in the origins of life. And Miller got quite famous for this. I think he was a student in the 50s when the work was done. This is him more recently, perhaps looking a bit tired of the attention that's been given. Also, lightning fixes nitrogen on Earth, which is important for agriculture, and looking to other planets. The electric fields, which are a sort of precursor to lightning generation, accelerate electrons and cause ionization acceleration, and that sort of helps with chemical processes on Mars as well. Finally, it's a sort of maybe an obvious point, but lightning indicates severe weather and that you have convective activity in clouds. So it's the presence of lightning is a good indicator that you have this particular, active weather systems going on. So how do we detect lightning? Well, the sort of most well-known way is through its optical signatures. So the lightning channel is very hot, and that causes optical emissions, a flash of light. And the gases in the atmosphere become excited by the heating energy of the lightning, and this causes them to emit at characteristic wavelengths. And lightning detectors on spacecraft tend to look at a portion of this with a filter. They look at a particular wavelength. They don't look at the broadband, which is really just to avoid other random flash lightning. Terrestrial lightning excites nitrogen, and nitrogen is obviously the most abundant gas in our atmosphere, but actually on terrestrial satellite cameras, they use an oxygen line, which is sort of stronger and more easy to detect line in some ways. And for about the last 30 years, there has been Earth orbiting lightning satellites. So here's a nice NASA map of global lightning from 1995 to 2013 with the two types of lightning sensors that they've flown. And quite recently, in the last few weeks, Europe's launched lightning camera as well. EUMETSAT satellite is now working, I think. And so if you want to detect lightning at other planets, you need to know what wavelength to look. This is based on lab experiments. So for the terrestrial planets, Mars and Venus and Earth, this oxygen line is probably the best one to use. And I thought it'd be fun to see what color it is. It's actually quite a dark red. It's quite close to being infrared, I'd say. In the gas giant planets, Jupiter and Saturn, they have mainly helium and hydrogen atmospheres, and this means a different wavelength is actually expected to win, this brighter red. And that's not actually been done for the gas giant planets, but that's what we expect to see, whereas Earth satellites have definitely seen flashes in this wavelength band. This is probably your favorite part of the talk, I guess, given the name. You can ask me hard questions about it later, I expect. So lightning emits radio waves. That's because there's an ionized channel where the current flows, that acts as an antenna. And so for Earth, the peak's at about 10 kilohertz because the lightning channel is typically 3 to 4 kilometers long. So the emission frequency, peak frequency, roughly depends on the size of the discharge. And that means you get planet-to-planet variations in the radio spectrum from lightning. If you have smaller scale discharges with shorter channels, and they emit a higher frequency than the longer channels. And the propagation distance also depends on the frequency. So all these have to be taken into account when measuring lightning at another planet. And this graph here shows that if you were in a spacecraft, let's say just outside, just in orbit of Earth, and you wanted to look at radio signals from different types of thing, it is possible to detect Saturn lightning, which has this quite small signal. It's still lower than a lot of other things, but it is possible to detect Saturn lightning, the radio signals from Earth. And you may be familiar with the Jansky, but it's a very small unit, so these small signals. And Uranus lightning is predicted to be reasonably detectable from Earth as well, so I'll come back to that later. I said that was if you were outside Earth's ionosphere. Of course, the ionosphere, the upper layer, affects the remote sensing possibilities, and if you were in Earth's atmosphere, you wouldn't be able to see any of this. You'd only be able to see a little bit of the detection. But having said that, Saturn lightning has been detected from Earth with radio telescopes, so it is possible. But clearly, it makes sense to be outside Earth's ionosphere. A slightly less well-known form of emission from lightning is a very low frequency signal, which is just a few hertz, which is within an atmosphere. And the lightning excites a resonance between the surface and the ionosphere, and it's called the Schumann resonance. So it depends on the size of the planet. It's 10 hertz or something like that. So this might be a novel approach to lightning detection. I'm not sure whether that signal would be able to get out of a planet's ionosphere at all. It might be interesting to hear your views on that. But certainly if you're within the planetary atmosphere, you could look for these Schumann resonances, and that would also indicate there was lightning there, as well as these other radio signals. So you will probably know that all radio waves are also magnetic signals, and this means that lightning radio signals can travel in the Earth's magnetic field lines, and this makes a signal, when you convert it into sound quite like a whistle, and that means you can detect whistlers from lightning by magnetometers. And I have an early recording of, I haven't set up my audio, hang on. Oh, I'm not sure the audio share will work because I don't think I turned it on when I started sharing. I'll try this and you'll have to tell me if it's terrible. I'll just try it now. You can't hear? Not very good. Okay, maybe I'll come back to that at the end, because otherwise I have to unshare and change the settings and share again. Sorry about that, I forgot that earlier. But you can hear this whistler sound from magnetometers. Not again. Of course, lightning also makes a sound, and the sound is called thunder, and it's a pressure wave formed by the heating of the air in the lightning channel. This is only detectable reasonably near the storm, so you have to be in an atmosphere to detect it. You might be surprised to learn that here on Earth, we still, thunder days, quite old-fashioned way of recording lightning, are still used at weather stations around the world. There's no agreed lightning detection mechanism for other than thunder days. So if a weather observer hears thunder at their site, and one day they mark it and it's marked as a thunder day, and that's how long-term lightning records are done on Earth, despite, the satellite things are only relatively recent. In other planetary atmospheres, the sound propagation depends on the atmospheric properties. Expected to be quite good on Titan, where the atmosphere is quite dense, and less good on Mars. So that's been predicted, and people have listened for thunder in other planetary atmospheres. So just to summarize that part, so detection of planetary lightning. So we expect lightning, we know lightning makes optical, electromagnetic, and acoustic signals. If you're on Earth, you can, I didn't mention this, but you can use a telescope to try and look at optical signals from planets. This has been done for Venus. Controversially, people can't agree whether it's detected or not. You can use radio telescopes. If you're in space, you can have a camera. with or without a filter. Often it's easier to look at the night side of a planet because the contrast is better. And you can use radio receivers or magnetometers to search for electromagnetic signals. If you're inside the planet's atmosphere, you can expect to see visible transients from lightning, and the radio signals are still there. They'll be stronger the nearer you are to it. You can also measure electric fields and thunder with a microphone. You might want to think about what constitutes a detection of lightning. If you just pick up one of these things at another planet, is it enough to say that you've detected lightning? And I think the answer is probably not. I think you need a couple maybe of those detections for people to really believe it's lightning. Otherwise people argue and can't agree and say it was a meteorite or some noise or something like that. So that is why Martian lightning and Venus lightning are a bit controversial. So I'll come on to that shortly. So moving on now to detection, extraterrestrial lightning detection. The first extraterrestrial lightning detection was Jupiter, and it was Voyager 1 in 1979, and it detected it was just a normal camera looking at the night side, saw these flashes of lightning, also detected aurora. So this is quite a good photo indicating the first detection of lightning and aurora in any other atmosphere. And the radio receivers also, the magnetometer, sorry, also detected whistlers. And the lightning's deduced to be about 1,000 times more energetic than terrestrial lightning, but sort of flashes per area per second or whatever, there's less, the fewer flashes. But it's about 10 to the 12 joules per flash rather than about 10 to the 9 on Earth. And there's something a bit weird about the radio signals from the Jupiter lightning, and they don't seem to get out of the atmosphere as well as we might expect. So there's relatively few detections of radio detections of Jupiter lightning. Its interesting point is that there have been many missions to Jupiter, and most of them have detected lightning in different ways. The one there at the moment is called Juno, a NASA mission, and it's got lovely cameras, really nice pictures. I think I've got one on the next slide. And it's so on this Voyager one, this was like the best camera Voyager had. But on this left-hand picture here, this is the Star Tracker camera, which is the least good camera on the spacecraft, which is used for engineering purposes, for navigation. And you can see it's also detected aurora and lightning. If you look at the detail, it's so much better than the best camera was 40 years before that. Just shows you how much the technology has come on. So here is a picture from Juno. I think that's false color, but the shapes are the same. It's really lovely, showing all the clouds and weather on Jupiter. There's ammonia clouds and there's this banding. There's really active weather, and that causes the lightning. So most lightning it seems to come from relatively deep within Jupiter's atmosphere, containing water and ice clouds. So we think the lightning comes from an Earth-like mechanism, because we know the lightning comes from roughly the part of the atmosphere where we expect these thunderclouds to be. However, recently there's been a new type of lightning discovered on Jupiter by the Juno mission, and they're calling it shallow lightning, so it's much kind of higher up in the atmosphere than they were expecting. And it appears to be generated by a different mechanism to the ice and water and snow and stuff that I've been talking about previously. It comes from ammonia clouds. So there's a mixture. This looks like a thundercloud on Jupiter, and it kind of is, but it doesn't just contain water, it contains ammonia. And then just like on Earth, you get this mixing of water and ice forms and stuff. But a bit higher up, you get this ammonia getting involved, and you get these sort of ammonia, a bit like ammonia hail, I suppose. And they call them mush balls, and they transfer charge through collisions, just like hail and Graupel does on Earth Earth thunderclouds. So this is quite exciting because it's the first time sort of ever that a new type of lightning has been spotted that we don't already know on Earth. So all the other types of lightning in space we sort of see on Earth as well. So Mars is dusty and it's like volcanoes, and the other planetary lightning is in ice water clouds, but this is different and special, and it's very new. So that's a very exciting finding from Juno. And just lightning detection is now so kind of commonplace on Jupiter that they use it as an indicator that there's weather going on, of rising air. So they just use the lightning to help understand what's happening with weather systems. There's also lightning on Saturn, which has been detected by the Cassini mission. This was detected by radio emissions, and they were sort of localized to particular storms, and they ended up being photographed. It took a while for there to be simultaneous radio detection and photographs, so there was a bit of debate about whether it was a real thing, but eventually they got those sort of coincident detections. And actually, additionally, a radio telescope on Earth detected the emissions at the same time again, so you've got 3 detection mechanisms to confirm the lightning. On Saturn, the storms mainly live near the equator and around 35 degrees north and south. Not sure if it's really understood why that is. And amateur astronomers are very helpful for this sort of work because they can help to track these storms. They're quite long-lived. The longest one lived for almost a year. And people, professionals are sort of arguing for like 3 nights on their telescope. They can't track something for a year, but an amateur person with a good telescope in their garden or whatever can do that. So that's very helpful. And the emissions overall are a bit weaker than Jupiter lightning, but they're stronger than Earth. And just for scale, here's a picture of a lightning storm here, and this is the same size as Earth, so they're big storms on a big planet. In Mars, things are a bit different. You get wind, it's quite windy, and the wind lifts up loose material. This blows dust around, and occasionally you get a big dust storm, which can cover the whole planet. So on the right, you can see the features on the planet are obscured by dust. And these are probably actually quite important for the Martian climate. Just like on Earth, there are dust devils as well, which is swirling vortices of dust. You've probably seen video clips of them and things for Earth. And on Earth, we know that dust devils become electrically charged by the kind of rubbing, the lofted dust. You can measure the electric field in dust devils. And on Mars, this is thought to happen as well. So here's a little nice video of a dust devil on Mars moving. I think there are better videos than that now. So on Mars, we expect to see lightning in these dust devils. Why do we expect to see that? Well, there are a few reasons. Firstly, it depends on the breakdown voltage in the atmosphere, which is the voltage you need to get a breakdown. Because the Martian atmosphere is low pressure, this means its breakdown voltage is very much lower than on Earth, and that means it's easier to get lightning. So you could have the same dust devil with the same size and stuff on Earth and on Mars, and on Mars it would have discharges in it. On Earth it wouldn't. It'd just have an electric field, but that electric field wouldn't be enough for there to be breakdown. Also, people have done lab experiments and seen flashes, and also people have done modelling and expect to see them. But despite this, the lightning has not ever been seen on Mars. This is an artist's impression, I should say, it's not a photo. So there's a glow at the bottom of that dust devil, which is thought to be what the lightning's like. So why haven't we seen the lightning? We expect it to be quite small because it's in these dust devils and potentially also in the storms, but there'll be sort of local areas of positive and negative charge. It's not as organized as a big thundercloud. So the channel for the lightning would be quite small scale, possibly not even a lightning spark at all, more just like a glow discharge. So these will be weak, as in that picture, it's more of a glow. And this means, of course, because they're in dust, they will be difficult to spot optically. They're just going to be weak and they're hidden behind a lot of dust. So perhaps it's not surprising we haven't seen this. There's been some work to attempt to look at microwave signals from lightning on Mars by radio telescopes on Earth and also spacecraft going around Mars in orbit, but they've been pretty inconclusive so far. There's not really any findings that are believed about how there really could be lightning. So I think it's out that it's not yet been seen. And so far, the only real evidence we have is that the dust is sticky and it sticks to stuff. Here's got an old picture of it sticking to the wheels of a rover. There are newer pictures of dust sticking to solar panels on the more recent missions, which can cause issues for its power. So clearly, it would be nice to go to Mars and get some in situ measurements to really work out whether or not there's lightning on Mars. But unfortunately, all the Mars missions carrying atmospheric electricity sensors have actually failed. It's been really unlucky. And most recently, there was an electric field sensor on the Schiaparelli lander, which crashed. It was called Micro Ares, and it didn't work. And then the ExoMars mission was carrying some relevant instruments. There's an instrument called MEGRE, which had a lot of magnetometers and electric field antenna. They should have been able to detect lightning if it was there, we think. And there was also an instrument called Dust Suite, which I think was going to measure the charge on the dust. However, unfortunately, this was on the Russian part of the mission. and it was cancelled. That part has not happened. So ExoMars is an orbiter and a lander. The orbiter's in orbit around Mars already, that's European. The lander was the joint European-Russian thing, and it's been cancelled because of the war in Ukraine. So that is not happening at the moment. In lieu of that, me and some people at Bristol have got a project where we're looking for magnetic signals from charged dust to try and help people search for lightning in the charged dust. Because if you've just got a magnetometer, you don't really know what to look for with this charged dust. There's very little done on it. So we're doing some lab measurements. My student has set up a rotatable dust. It's a bit like a food processor for dust. It's swirling around the dust at the bottom, and we have an electric field sensor, and we have some charge sensors at the bottom here. You can do two things. You can drop dust through it, and we measure the charge of the dust as it falls, and you can do sort of whirling experiments to try and loft the dust to be a bit like a dust devil. And we're trying to look for electrical and magnetic fields from the dust. And there's also a lander at Mars at the moment, which is called InSight, which is more of a kind of geology mission, but it has got a magnetic field sensor, and it can detect dust devils. So we're also looking at that data to see if there's anything there. So that's quite interesting sort of ongoing work that we're doing at the moment. Moving now to whether Venus could have lightning. So people have been quite excited by the idea that Venus might have lightning for a long time. And the Russians sent their Venera probes to Venus in 1980s and 70s. And they all work quite well. And they had various electrical sensors, which were sort of suggestively thinking that there might be lightning. Nothing really conclusive, but suggestive things. And more recently, there was a magnetometer on Venus Express, and it's interpreted the magnetic observations as whistlers for lightning as well. But the lightning flash rate that they come up with, Russell et al., is really a lot of flashes, and they've never been seen. So that's a bit strange. And also, a lot of the spacecraft that went off to successfully detect lightning at Jupiter sort of pointed their cameras at Venus when they went past, but they didn't see anything. So that is a bit strange. And there's currently a debate in the scientific community about what's going on. So how would you get lightning if there was lightning on Venus? Well, it's not really clear, because the clouds aren't made of water, they're made of sulfuric acid. And then you don't have any ice or hail or anything in them. So how would they generate lightning? We don't know. And also the breakdown voltage would be really big near the ground, because the air pressure is about 100 times more than it is on Earth near the ground. So you probably wouldn't have cloud to ground lightning, which is why I find this video clip slightly irritating, although it's still quite fun to watch. I think this process is actually impossible that the artist has put in there. So as I said, if you had Venus lightning, we don't know how it would be generated. And also a further point that's arisen from modelling is to do with the clouds conducting electricity a bit better than you might think. And if the clouds conduct electricity, that means the charge just leaks away. You don't get this separation that you need for lightning. And that might be another reason why it's difficult to get lightning. Also, if you do have lightning, where is it? I've just said cloud to ground doesn't really work. I think people are quite keen on the idea there might be sprites in Venus's atmosphere. There have been some lab measurements which would show what they look like at the top here in sort of simulation of Venus's atmosphere. And obviously it would be above the clouds. So Venus has a very thick cloud layer, which will make it hard to see lightning. But if it's above the clouds, it might be a bit easier to detect. And we know the volcanoes on Venus, so could volcanic lightning perhaps be relevant? We don't know. There's a Japanese space mission at the moment to Venus, Akatsuki, and it's looking for lightning. It's got a lightning camera with a filter on the same wavelength that we have for Earth. And so far it's seen one flash. And this flash is currently not published in the literature. And I think there's a bit of argument going on about whether it's a real flash or whether it's a meteorite. So the jury's very much out about Venus lightning. Although we're working on it at the moment to try and be in some colleagues with Venera data, amongst other things, to try and work out what's going on. So moving out very much further now to the ice giant planets, Uranus and Neptune. Voyager 2, the famous 1970s, 80s space mission, is the only spacecraft to have been to these planets. And it had cameras and it had radio detectors. There were no optical signals, but there were radio signals. And it was fairly strong, fairly clear at Uranus. They detected lots of quite good transients, which they called UEDs, Uranus electrostatic discharges, and they were quite strong. And then on Neptune, it's much more marginal. There were fewer detections and it was weaker. They did detect some whistlers. So I think loosely people do agree that there is lightning at these planets, and also it's known that they have water clouds deep within their atmosphere. So there is a mechanism that could work. Although we don't really know that, we've not been able to look that far down, but models suggest there are those clouds. But there are many things that are not understood, and it would be very good to have another mission to these planets. In particular, Neptune has sort of internal heating, like Jupiter, and that would suggest that convection is quite good. That would kind of suggest the lightning would be stronger on Neptune and Uranus, but that's not what we see. So that's strange. One of the interesting things about Uranus is, as I hinted earlier, it's quite a promising candidate for ground-based detection due to the radio spectrum expected. And there's a radio telescope that has been looking for it, but unfortunately this radio telescope is located in Ukraine, and eastern Ukraine at that, and I'm not sure if it's still there anymore even, but it was looking for lightning on Uranus, and they did do a few campaigns. They hadn't seen it, but I would hope that it would be possible in the future to look for Uranus lightning from radio telescopes from the ground. So just to summarize what sort of the detections are. So yeah, I was saying Venus and Mars not confirmed at all. People have looked quite hard for Venus and Mars lightning, but it's still not confirmed, particularly with Venus lightning. Actually, there are many attempts, but they're not consistent, and it's not confirmed. Mars is more like we expect it to be there, but we haven't seen it yet. But there haven't really been any in situ measurements, and I suspect that once there are some, they may be successful. Jupiter and Saturn have a lot of lightning, and Titan, which is Saturn's moon, that was thought to have lightning, but it's not been seen. Uranus and Neptune probably do have lightning, but there's been no optical detection. So there's lightning on many planets, but there's still many things we don't understand about it. Now I'm going to move on to the second part of the talk, which is about non-thunderstorm electricity. And this is about cosmic ray ionization. As you probably know, galactic cosmic rays are energetic particles that are created by sort of explosions in space, supernovae, and so on. And these energetic particles are everywhere. They whiz through. When they get to an atmosphere, gas molecules, they interact with the nucleus of gas. I said molecule, but it only needs to be an atom. And they cause a kind of cascade of subatomic particles, many of which are ionizing, and there are different families of particles here. So here are the muons that we were talking about. They're the most energetic ones, and you also have electrons and gammas, and protons and neutrons. Neutrons are non-ionizing, but everything else does ionize. So with height, you get this typical atmospheric ionization profile. You get this kind of bulge, this peak in the ionization, which is where you get most of these secondary particles, and they kind of run out of steam as they get further down. And that's triggered by the atmosphere kind of getting dense enough for most of the cosmic rays to interact with the atmosphere and cause this cascade. And the cascade for Earth, we call it the Hertz-Wegener maximum, the maximum location of this peak. It used to, until quite recently, it was called the Hertz maximum, but Wegener was incorrectly not credited for it because of being Jewish and it being around the time of the war. So now it's good that they are both recognised, Hertz-Wegener. So it's not just cosmic rays, although cosmic rays are everywhere. You can have radioactivity coming from rocks. We get quite a bit of that on Earth near the surface. You can have UV radiation from the sun. You get less of that on Earth because it's absorbed by the ozone layer, but in other planets don't necessarily have that, so they have UV photoionization. And occasionally, if you're near enough to the sun, space weather events will happen. The sun will throw out a lot of particles and they will create some ionization, normally at the top part of the atmosphere. Very occasionally, for big space weather events, they can get down to the surface. What does ionization do? It creates ions and electrons. Depending on the gases in the atmosphere, sometimes you get ions, cluster ions. So sometimes electrons will just stay on their own in the atmosphere. But in some atmospheres, there are enough gases around, they just stick to the electrons, so you don't get free electrons. So in Earth's atmosphere, near the surface and up to about 60 kilometers, you don't get free electrons at all. They just stick and make negative ions. And then these clusters, you get little bundles of ions, but they're still charged. But some atmospheres just have free electrons in them, and some have both. But what do? They make the air conduct electricity a little bit. And this conductivity increases with altitude because you have more cosmic rays the higher up you go. So what's the effects of ionization? What does charge actually do? Well, ions and electrons can have a whole range of effects. They can cause particles to grow, which loosely we call ion-induced nucleation. If you look at the detail, there are several different mechanisms. Ions can stick to particles and cause them to fall out. If you have an ionizer in your house, for example, you might find it gets kind of dirty around it. That's because the ions stick to dirt as sort of smoke and certain stuff in the air, and then it settles out. That's scavenging. If you have cluster ions, they have hydrogen bonds in them, and then you have this absorbs infrared radiation. And also, if you have free electrons, there can be chemistry that's driven by those free electrons. So these effects sort of take varying levels of significance depending on where you are. So places like Earth, we have a lot of weather. We have the sun. It drives weather systems. So these other effects tend up being quite small in comparison to sort of normal weather, if you like. But if you start getting to places where there's not much solar radiation, then the charge effects become much more important. And this is particularly relevant at the outer planets, which get much less solar radiation. An example of this is Triton. When Voyager went to Neptune, took a picture of Triton, which is Neptune's largest moon, and it found they had clouds. It was really unexpected. It's got very sort of thin ice clouds that look like cirrus clouds. Well, it's really cold, so they're not water ice, they're a nitrogen ice. And so far, the only explanation for why those clouds are there is to do with ionization and sort of the clouds forming on the ions. So that's just an example of how these processes that aren't necessarily important on Earth can be important in other planetary atmospheres. So if you want to look for ionization effects in planetary atmospheres, obviously it's a bit easier to do for Earth. You can measure the ions and you can measure cosmic rays and you can measure the clouds. Further away, that's much harder, particularly without in situ detectors. One of the techniques we can do is look at the cycles of ionization and how they are modulated. We know that cosmic rays get deflected away from the solar system by the sun because the sun's magnetic field bends these charged particles away. And so there's a solar cycle in cosmic ray ionization. It's in antiphase to the solar cycle. So when it's solar maximum, you have more sunspots, you have fewer cosmic rays. So that's one of the techniques we're able to use to look for ionization effects in planetary atmospheres when we can't get to them. The only actual measurements of this, what we so call the Earth, we call it fair weather electricity, non-thunderstorm electricity, were made by the Huygens probe that went to Titan in 2005, and it had some air conductivity detectors. It also had a microphone, which was looking for thunder, didn't hear any, and some particle detectors. Basically, they roughly worked. There were a few issues. You can see them. They're on this boom here. That's the lander, the main body of the lander, and then at the sides you have the detectors, which is separated. And it turned out that Titan's atmosphere is much more complicated than first thought. So it's taken many years to analyze the data, and I've got a bit more about Titan later on. But the profile of conductivity and ionization sort of follows the shape that you expect, roughly, that I showed earlier from the first with the first Regner maximum and so on. Now thinking about Neptune, there was a proposal that clouds are actually formed in Neptune's atmosphere by clustering onto ions formed by cosmic rays. So you have these ions which are made by the cosmic rays, and then they do some chemistry, react with hydrogen and methane, and get this sort of, I don't know what it's called, methane plus hydrogen ion. And actually then methane, neutral methane, can cluster onto these ions. It's made easier for their particles to grow because it's a charge in the middle. Now, this is actually the same mechanism that happens inside a cloud chamber. I don't know if you've seen a cloud chamber. I have a video of one here. Yeah. So this is it's a supersaturated gas in a pressurized chamber, and then cosmic rays come in, and it's some sort of alcohol supersaturated inside the tank, and you get condensation onto the tracks from the cosmic rays. So those short stubby tracks are from things like alphas, from radioactivity. The longer, thinner tracks are from muons. and some of them decay, and you can see these kind of swirls they make. That's because they're actually decaying in the tank, and then you're getting their tracks visualized by the cloud formation. But this is impossible in Earth's atmosphere naturally. So on Neptune, you're seeing another effect that you don't see on Earth. And this mechanism actually contributes to an 11-year solar cycle in Neptune's clouds, a long-standing set of observations that hadn't really been explained. And I was very pleased to be involved with explaining this signal and saying it was cosmic rays. And we actually also found a similar effect in the atmosphere of Uranus. So this is the first evidence that you get this cosmic ray cloud formation in two planetary atmospheres, and they're both linked, coupling by this magnetic connection to the sun. Thinking now about joining up the joining up the sort of lightning with the fair weather, so-called electricity. This is the idea of a planetary global electric circuit. So this is an example for Earth. On Earth, it's probably easier to explain for Earth to start with. You have thunderclouds, and you have this charge separation, and lightning and charged rain as well return charge to ground, and you end up with a net charging up of the upper atmosphere, the ionosphere, with respect to the ground. And so the ionosphere is reasonably conductive, and the surface is reasonably conductive, and the atmosphere is not very conductive. It's like a big resistor. So what happens is you have these regions of charging where you have thunderclouds, but everywhere there's this drift current of ions, the ions that are formed by cosmic rays. They drift down, and there's a net drift of positive ions towards the ground. And that means that you have an electric field which is present in the atmosphere everywhere away from thunderclouds. So if it's bad weather, if it's raining or something, or if it's like smoggy or something like that, then you can't see this sort of global variation. But if, for example, you could go out and measure that today, when it's been a nice day, you would see there are about 100 volts per meter in the atmosphere. So this idea was suggested by C.T.R. Wilson in the 1920s. He actually invented the cloud chamber that I showed earlier in about 1900. He became very famous in particle physics for inventing the first technique to visualize a subatomic particle. But actually, he was obsessed with the weather and atmospheric electricity. He worked on that for his whole career, but he got the Nobel Prize for the cloud chamber. His atmospheric work was recognized less. But we in the atmospheric electricity community like him, and he has a Twitter feed from Beyond the Grave where he comments on all matters to do with atmospheric electricity. And we have a mailing list, and we have events. So if you're interested, you can sign up for our events. Some are online, some in person. So this idea of a global circuit was suggested first by C.T.R. Wilson, and he was able to explain the electric field that's present in the atmosphere away from thunderstorms by this, and a constant current that's flowing that's quite small, but you can measure it. The idea of extending global circuits to other planets was proposed by someone in the States in their undergraduate dissertation in the 1990s. I also did an undergraduate dissertation in the 1990s, but it unfortunately wasn't as good as that one. It was quite dull. So this guy filling in suggested this global circuit for another planet idea, and I've kind of developed that and to think more about planetary global circuits. So why are they important? They provide a direct link between the top and the bottom of the atmosphere over about 100 kilometers. Very few things do that. And this current flow, this means there's an organized flow of these ions. So there are ions from cosmic rays, but they're not just floating around, they're actually moving in a coherent way. And this means they may have sort of small yet detectable effects on the radiative balance of the planet. So things like whether or not it's going to rain from a cloud is related to the charging. And also you get charge building up on the edges of clouds, and this affects the lifetime. My colleagues at Reading University do a lot of work on this, and they do balloon launches through clouds, and they've detected some of these effects already. So if you want to have a global electric circuit in a planet, what do you need? You have to have an ionosphere, or a conducting upper layer and a conducting lower layer, and you need some ionization. I mean, I've been saying you get ionization everywhere, so that's a kind of given. And you also need convection or some sort of similar charge separation mechanism. So we can go on to think about whether other planets have global circuits. This is the Mars global circuit model. This is the filling in dissertation, and later developed by some other people in the States. So it's you can see it's quite like the Earth idea, except instead of a thundercloud, we have a dust cloud, and it charges up. and you have some ions that are flowing in the circuit, and you also have some electrons. So this kind of is quite a similar model to Earth. It's a little bit, I mean, there are things about it that are different. In particular, the circuit very much depends on how many dust storms there are. So if there's one of those massive planet dust storms, the circuit's quite kind of active, the electric fields are bigger, but if there are just a few dust devils, the electric fields are smaller. But it's a similar model to Earth. So we could start to think, well, Jupiter's got lots of lightning. Does Jupiter have a global circuit? What might it tell us about Jupiter if it had a global circuit? Does it have charge separation? Yes, it does. Ions, electrons, yes. Does it have a conducting upper and lower layer? Well, we know it has an ionosphere. The lower layer, however, is a bit weird because it's a big ball of gas. And if you go deeper and deeper inside, I mean, it's hydrogen atmosphere, then you get to very high pressures, the hydrogen starts to act like a metal, and that's a conductor. And it turns out that where that metallic hydrogen kicks in is actually so deep in the atmosphere that the cosmic ray muons don't get there. So that means the muons are very energetic and they can go a long way, but they can't get all the way into Jupiter's atmosphere without losing all their energy. And that means you don't have ionization down to the surface. And I think that means that the conducting lower layer, the charges can't get there. So perhaps that means that there's no evidence for a global circuit, or if there is, it's quite different on the gas giant planets. Back to Titan, I had to mention this because it was just so sort of rich in terms of atmospheric electricity. It was very complicated and it had some surprises. The lower atmosphere is much more electrically complicated than they were expecting because there's a mixture of free electrons and ions and aerosols. And that's more complicated than I think we've seen elsewhere in the solar system. Also, the Cassini spacecraft that was orbiting Saturn and did a lot of flybys of Titan found that there were a lot of charged particles in the upper atmosphere, like cloud-style particles, not particle physics particles, like micron-sized particles. And these contribute to the haze. You might have seen pictures of Titan, it's got a kind of orange haze. And so charge is sort of very important for this haze production, which again was a completely unexpected result. So you might think, is there lightning or another route to charge up a global circuit? Lightning was predicted before people went to Titan, but it's never been observed. And Cassini has done 100 flybys and not seen any radio signals from Titan lightning, even though it's seen lots from Saturn. And the microphone didn't hear thunder. This artist's impression, maybe I'm a bit harsh. I said this was a fanciful artist's impression. I don't think it's as fanciful as some of the other ones we've seen today, but it does have lightning and clouds and rivers and stuff. But Titan does have rivers and things. The Huygens probe observed quite a low frequency signal at 36 hertz, and people were quite excited about that, and they called it a Schumann resonance. And there is definitely a 36 hertz signal in this data. But I think subsequently it's been thought to be caused by actually a weird kind of coupling with Saturn's atmosphere, which is nearby, rather than the Schumann resonance that's excited by lightning. So far there's no evidence for lightning on Titan. But despite this, there is still quite some interesting atmospheric electricity. There is rain. There's definitely rain on Titan. It's been detected. It's not made of water. It's made of liquid methane and ethane. And because there are electrons in Titan's atmosphere, when the drops fall, they will become charged. So there's possibly a route for a global circuit on Titan involving charged rain, but perhaps not lightning. So you can build up this idea of like maybe a global circuit on Titan. So you have the cosmic ray ionization, as we thought, so ions and electrons. And then you have this weird haze, which is charged in some way. So there are some clouds in sort of away from the stormy regions. There's just this haze and it's thought to settle downward, but it's charged. So maybe that acts a bit like the current carriers, who knows? And then in the sort of disturbed weather regions, we know there are convective clouds, a bit like thunderclouds, but they don't appear to be as big and as active as the clouds that generate lightning. But they are thought to, well, they rain, and there's possibly they may get charged, we don't know, in which case there may be corona discharges and things like this. So, and then you also have clouds made of ethane and methane, and they charge up and they drizzle. So there's a very complicated electrical environment on Titan. And everything will get negatively charged because they're electrons, all the particles. So it is possible there might be a global circuit on Titan, and that would be driven by rain, probably, although there may be lightning that we haven't seen yet. And it probably involves this haze as well. So it's a very complex picture, and there's a lot still to be understood about that. Coming to the end. So lightning is pretty common, and it's been detected at the majority of planets with atmospheres. Conclusive optical detection is only being seen at Earth, Jupiter, and Saturn, but there's radio detection at the outer ice giant planets. Non-thunderstorm electricity is present everywhere, but these sort of important effects from charged particles, I would say, are only really at the outer planets. And this global circuit idea, we can say that Mars and Titan and Earth and perhaps also Venus have a global circuit, a bit like the one on Earth. Gas giant planets sort of appear to have quite a lot of the ingredients needed for a global circuit, but possibly not in the way that we understand these terrestrial planets to have it, because of the gas nature and the way that they become conductive only very deep in the atmospheres. So here's a summary, which was generated as part of this paper that I've recently published in the Royal Astronomical Society's magazine. So which of the planets have global circuits, which have lightning, which have the fair weather effects? Definites are sort of in black for the lightning and fair weather effects, and possibles are in grey. So the outer planets, Uranus and Neptune, they definitely have lightning and definitely have sort of cloud formation effects. So they're very interesting in atmospheric electrical terms. Titan and the terrestrial planets have this global circuit, and some of the other planets have lightning. And Venus, we're very much under discussion still at the moment. Just finally, I thought I should mention exoplanet lightning, because someone will no doubt ask me about it if I don't. There are lots of exoplanets known now, many thousand. I haven't checked the numbers recently. Last time I checked, about 3 months ago, it's probably about 5,000. So lots of them have clouds, and there are just so many that it seems likely that some will have lightning. People tend to use solar system analogies to estimate the flash densities. We're not clear, of course, how you would detect that, because the signals would be so weak. They're so far away. Even really powerful lightning would probably have a weak signal. So I'm not sure we know how to do that, but there are just so many of these planets that would have lightning, or could have lightning, that would be a bit like the gas giant planets and the Earth ones and the Neptune ones. And of course, they all have cosmic ray ionization, so there's going to be a lot going on. So with those planets, I think if you were going to detect electrical effects, it might be easier to do it via the radiative properties, sort of the clouds and things which have been seen, but that would be complicated. So there's a long way to go in detecting atmospheric electricity outside the solar system. So just to finalize, tell you about some further work and upcoming missions. Upcoming missions are NASA's taking its quadcopter thing to Titan, called Dragonfly. That's not got any atmospheric electricity instruments on it, but it does have things that will be useful for atmospheric electricity. And ESA, European Space Agency, is going to Venus, Envision. Envision is more of a geology radar type mission, but there will be some capability to detect lightning on the instruments there. So that, again, will be very interesting. In the meantime, we're stuck with theory and modeling and lab measurements. And these are some of the things I'm working on. Most of these, I've got people working on quite a lot of these problems. Venus cloud charging, and we're doing the lab experiments for Mars. And previously have done some Venus cloud simulations as well in the lab. So just to summarize, electricity has been in Earth's atmosphere for as long as we know of it. It's been measured for maybe a few centuries. In space and other planets, we've known about atmospheric electricity for only about 40 years, but we see that it seems a fundamental part of many atmospheres. So we can conclude that electricity is a key property of atmospheres. It's a unifying concept, bringing together different parts of the atmosphere and different parts of science, and may even link to the origin of life. So I'd like to acknowledge various collaborators and draw your attention to my books, which are available on online stores. Actually, seriously, on the book, this one, I'll show it here because it's come out now. That hadn't come out when I wrote the slide, but this electrostatic phenomena one. That's the most friendly book if you are interested. The others are a bit more academic, experty. Yeah, so thanks. That's the end of the talk. Thanks very much.
Thank you very much, Karen. Much appreciated. Now, questions. Either just unmute yourself and pipe up, or type them into the chat line.
Hello, Karen.
Hello.
The book that you just recommended, is that appropriate for radio astronomy, or would you recommend one of the others? What do you think?
It's got a little bit about radio detection of lightning in it. I mean, it's not, yeah, a bit. I'm just thinking which one would be best. If you want something readable, that's definitely the best one to start with. And if you specifically want to read about radio detection of lightning, the more technical book, the one called Planetary Atmospheric Electricity, has more detailed technical publications in it, but I think there's one in there about radio detection. So if you're especially interested in radio detection of lightning, that's probably the best one to look at.
Thank you.
Well, if there's definitely silence, I'll have. Oh, sorry, Alan.
I was wondering if it was possible that there would be a planetary surface in the outer planets due to convection, with ions being drawn down lower into the atmosphere.
Yeah, there might be. It might be. I mean, the lower boundary is the thing that is not clear. But yes, I mean, there's convection and there's ionisation, so there might be something like that. But we're not clear exactly what goes down at the sort of bottom end of it.
Can I have one, Karen, and then I'll pick one up from the chat feed. You've mentioned various sources of charge within Earth's atmosphere. Stick with Earth for now. Within Earth's atmosphere, there's been persistent discussion, and I don't know where this has got to recently, that lightning and charge is released in earthquake events and movement of faults. What's the state of play in that? Mumbo jumbo or real?
Yeah, there is a bit of truth in it, I think. I think there's a lot of dodgy papers on it. But I think, I mean, I've written a paper on it, which I hope isn't dodgy. So it seems reasonable that when the rocks start moving prior to an earthquake, that you get release of radon, because that is in the Earth's crust. And then that causes a burst of ionisation, or it could do. And there have been anomalies detected that are consistent with that. And we proposed a model, and then, separately, there have been some changes in the ionosphere that are detected by satellites, like around the time of earthquakes. We came up with a mechanism involving the global electric circuit for how radon release at the surface would affect the ionosphere. I think there is something in it, but you have to watch it because there are so many papers that are just like, oh, we saw a light, and it was lightning, and it's kind of, no, it wasn't.
That's interesting. Thank you. I'm just going to pick one up from the chat. It's from Philip. Why does so little carbon dioxide in Earth's atmosphere reflect so much infrared radiation causing global warming? If you think that's too far off topic, please say.
It's slightly outside my area, but I think it's to do with it's sort of what I touched on, infrared. So if you have molecules, they're bonded by hydrogen bonds, and then those bonds can bend and stretch in different ways, and then they absorb radiation depending on the particular bending and stretching modes. So they do all sorts of, like, if you have a sort of molecule picture from school in your head, they all sort of jiggle around, and they absorb infrared radiation in particular wavelengths. And I think that is why carbon dioxide is an effective absorber of infrared radiation. And that's also how you can detect gases in atmospheres and in the lab and stuff. That's a quite important technique as well.
Does that mean that given the cosmic ray influx and the charges moving around have a direct influence on short-term climate?
I wouldn't go so far as to say this is something I've done. This is my own work here. I have measured small infrared changes associated with ionization from cosmic rays. I did it in the lab and I did it in the atmosphere. In the lab, we made the ions like artificially, and we measured an infrared change. And then we also did some experiments in the atmosphere where we had a cosmic ray detector and we looked at all the events, and then we found that there was a dip in infrared radiation. So, but it's a really small effect. So I wouldn't go so far as to say it affects climate, but there is something going on there.
Any more questions?
Oh, there's a question in the
Yes,
chat.
there's one in the chat. Oh, good.
Is it possible that some of the more exotic high altitude events could damage spacecraft? Yes. Space weather is a real hazard for spacecraft. Not so much with the sprites and things. I'm not sure the sprites go high enough to get to the orbits that the spacecraft would be at. And I think those sprites are quite kind of diffuse. So I think probably not so much. Yeah, if you had space weather stuff, that would throw in a lot of particles and that could damage the electronics in the spacecraft, and people do worry about that. Probably the sprites and elves are sufficiently spread out over a big area and a big vertical extent that they probably wouldn't be an issue for spacecraft. I would hazard a guess.
Do they contribute to heating in the upper atmosphere?
I don't think so. I think, again, it's also so spread out that they don't do that much. Is ball lightning real? Yes, I think it is real. There's so many observations. It's one of those things that sometimes people say that people are getting a bit overexcited and sort of imagining stuff. But there are quite a few very famous observations of it. There's one of the most famous ones was that some very important physics professor at Cambridge University saw it, and people believed him when he said he'd seen it. And there are quite a lot of observations. I don't think we really know how it's formed. I don't think that's known. There are a few theories, but not really sure yet.
Any more? Okay, I think we've exhausted the questions. Okay, we have what about comets?
What about them?
Yeah, would you like to elaborate, Richard?
And they do probably have charges on their surfaces. Could they have discharges? I don't know. Well, they don't tend to have atmospheres, but you can get discharges in a vacuum. But I'm not sure whether because they're just like balls of ice and sort of mushy snow type stuff, aren't they? I don't think there's many charge generation mechanisms. Yeah, Van der Waals effect, that does act to stick particles together on asteroids in particular, because it's small sort of rocky powdery stuff. So yeah, the Van der Waals effect is important at those types of body and sticking particles together, but it doesn't do enough, I don't think, to generate discharges. What kind of instrumentation is used to detect whistlers? I don't know exactly. I just think it's a magnetometer.
Karen, I've got to be really mean and just park that one and throw that out to the audience, because there are people in the audience who are very, very capable of answering that one. Meteors triggering discharges.
I don't think so, because I think they're too high up. They're much higher up than the thunderclouds. So the top of a thundercloud is maybe about 30 kilometers, and meteorites, obviously some get to the surface, but most of them don't. They're like 100 or 200 kilometers, so I don't think they would.
Okay. Go on.
Whistlers are ELF radio. You can pick them up with kilohertz order of radio detectors. Basically a sound card with an antenna on it will give you whistlers. Look out for lightning though. It'll eat your computer.
Yes, I was going to say an indoor loop antenna would be an appropriate device.
Very good idea. Yeah.
It's a bit safer.
Yeah. Or a small stub antenna outside. Doesn't take much of an antenna. A little high impedance transducer or transformer of some a high impedance input circuit of some kind to get you coupled to your sound card, and you're off and running.
Anyone else want to chime in on that one?
Oh, you also get the dawn chorus if you're having fun with the listening. There are a couple of groups that have to do with this that you can look up.
Yes, there is a very good natural radio website, and Renard, I've got his surname. There is a book entitled Natural Radio, which covers this area very well.
We have this in the UCRA bookshop.
I was just picking up some questions out of the comments feed. Somebody's mentioning cloud formation changing the albedo and being a warming thing. Can I just add to that noctilucent clouds?
Yeah, I'll do the bit about the albedo first. Yes, I mean, the cloud formation, I don't know if it drastically does, but it does. Certainly at Uranus and Neptune. I think we worked out there's about 25% of the reflectivity was 25% of the changes in the reflectivity were affected by the cosmic ray changes. And then I've got a PhD student who's looking at it for Venus at the moment, with space weather events, and he's seen some interesting stuff that he's working on. Yes, noctilucent clouds are a bit different. I think there is a hint of a link between cosmic rays and noctilucent clouds. I think it's more of a link between spacecraft emissions and noctilucent clouds, as I remember. Yeah, the stuff about the albedo, you have to be careful. I mean, for Earth, it's really, really, really small. I think, yeah, and we were looking at, it's like variations on variations, but I've published papers on it, and you can look at them and see the details for the albedo changes.
On about noctilucent clouds, I photograph noctilucent clouds quite a bit and create videos from them. And on a couple of occasions, I've noticed what appears to be thermals developing in the noctilucent clouds. Could this be a way of transferring charge to the upper atmosphere?
Yeah, maybe. Yeah, I don't know too much. I don't know too much about it. They're quite high up though, aren't they? They're already in the upper atmosphere, I think.
Yeah.
So I'm not sure if it would give you the linkage because they're kind of already there. But yeah, I'm not sure. It seems like they ought to be involved somehow, but I don't know exactly what happened.
Okay, for a third time of asking, are there any more questions? Right, I'm going to call it quits at that, and say thank you very much, Karen. It obviously was an interesting talk because you've got lots of questions coming at the end of it. I always think that is a nice sign of success. Thank you very much. Now, could I ask Jordan to unmute himself, say hello, and The floor is now yours.
All right. Hello, I'm Jordan Wilkin. I just finished my bachelor's at the University of Central Lancashire in Preston, UK. And so for my bachelor's project, we took a cosmic watch muon detector and we put it on a high altitude balloon. And so I'll pull up the PowerPoint now. Can you all see anything?
We can see your whole PowerPoint screen. I'm not sure if you've got a presentation started. Try sharing the other screen, or just press start the presentation. The
Right,
screen
well,
that
my screen has gone completely black now. I can't see anything, and so this is fantastic. Okay.
I suggest you just flick your slides through. They're quite legible, and we can see them.
Okay. Okay, so so Karen already talked about what cosmic rays are. So I'm just going to sort of skim through that then. But you know, like you said, they're high energy particles that come from space. So either stellar events or supernovae, things like that. Most of them protons. So that's what we'll be focusing on. This is sort of the map of what happens. So the proton hits the atmosphere, it collides with one of the atmospheric molecules, so primarily oxygen or nitrogen. And then that releases a whole secondary shower of particles. And we'll be focusing more on muons, and those come from the decay of ions here. So the detector itself is just a scintillator detector. So you have, you know, the solid slab of plastic scintillation material, and that's sitting on top of a silicon photomultiplier, or just a SIPM. And then all of that also sits on top of two PCBs, and then it runs the data into an Arduino Nano to log it, and then it goes to a micro SD card to store the data. So just a rundown of how a scintillation detector works. Essentially, the particle hits the material, excites it, and then when it de-excites, it emits a gamma ray. That gamma ray goes to the SIPM, and then that SIPM is hit with a photon and then releases electrons, and then it causes a cascading event, and then that causes a current, and that current is read off as a signal. This is what the detector looks like without the casing. So that's the actual scintillation material and black electrical tape. Underneath it is the SIPM and the main PCB. The balloon itself, that's fairly straightforward. It's just a big latex balloon that you fill with helium. But depending on what type of balloon you get, it can go from 20 to 100 kilometers up. Ours went up to 25 kilometers. And then they're typically utilized as well with GPS trackers for recovery. and then parachutes for the descent to make sure, you know, doesn't come plummeting down at Mach speed or anything like that. As for the protection from the elements, what we decided to do was we had an electric hand warmer that we sandwiched between the power pack and the detector itself. And then we just wrapped that in aluminum insulation that we got from a bag from Aldi, I think. Very, very cost efficient, I think. But it worked tremendously. But we'll get to that later. As for the actual preparation of it, we used an online flight predictor from Strato Flights, and it's fairly straightforward. You just put in your latitude and longitude for your location, the altitude that you're launching from, the time of day, what day you're launching, and it'll spit out some sort of flight path, as you see here. So I don't know how well you all can see this because it's not in presentation mode, but it was originally supposed to land over here, and that's where we originally drove to pick it up. However, there is a massive amount of error bar on this, and it ended up actually landing in Grange over Sands over here, which was quite frightening because we thought it was going to maybe land in Morecambe Bay and then we would just lose it, but luckily that did not happen. So we also had to get CAA permission. That's just standard procedure. We also made a procedure checklist and material checklist as well to make sure that we had a set schedule. We don't forget anything while we're setting it up. You know, tie everything down so that way if someone lets go of the balloon, it doesn't just go off without all the materials. This is what the setup looked like. You have the payload here in a styrofoam thermal insulating box. I have a camera mount here with the GoPro. And then there's a tether here that attaches to a carabiner that then goes through the parachute. And then that carabiner up there attaches to the balloon. For the tracking system, we have the GPS tracker, the logger, and then the radio transmitter. But we actually ended up not using the radio transmitter. We just used the GPS tracker because it was simpler and it saved weight. So here are the temperature experiments that we did on the ground. So we did 2 experiments outside, one without the electric heater, one with the electric heater. And as you can see, with the electric heater, it stayed warmer for longer. In fact, by the time we had gotten back to it after 3.5 hours, it still hadn't cooled off. So that was a good sign that showed us that the setup worked. It kept it at operating temperatures. We also took some baseline measurements here at an altitude of 24 and 55 meters. Strangely, the count rate at 24 meters was actually higher than at 55 meters, which is the opposite of what you would expect. But we will get to why we think that is in a moment. So at the actual launch, the altimeter took this data, and so you just have altitude as a function of time. And then if you just isolate the ascent curve, you can get a line of best fit, and then from there, you can convert time into altitude, which is what we need for the detector data, because the detector only detects events in time. It doesn't detect altitude. So that's exactly what we did in this plot. We just converted all of the time measurements to altitude measurements. And then to make it more digestible, we separate it into intervals of 500 meters. And as you can see, it follows a fairly parabolic path, which is not what you would see generally, but at lower altitudes, that is what you would see. But overall, it has a sort of bell-shaped curved that we'll see later. But the detector itself, unfortunately, turned off at around 7,500 meters. So we have no data after that from the detector. So that was a bit unfortunate. But we think we have a hypothesis as to why that happened. But even still, the data was very, very good that we got. So the reason we think it turned off was basically what we planned to do was to keep it warm so it didn't freeze. And what we think happened was the exact opposite. We think it got too hot because if you look at the temperature data here, it gets up to 40 degrees Celsius by the time it shuts off, which is pretty toasty. So yeah, so that is probably why it turned off. So in hindsight, don't crank the heater up to the max setting. But you can also see for the altimeter though, that was not actually attached to the heating element itself. The residual heat that was coming off of it was still a lot to keep it in operating temperature range. So luckily the altimeter didn't shut off. So as for the data that we actually collected, the little blue curve here in the lower left-hand corner, that is what we got. That goes all the way up to 7,500 meters. And then this data is from the Cosmic Watch creators at MIT. They did their own HAB experiments, and so we've kind of compared it here. And so at that altitude, it does match up with what you would expect. In the data from MIT, you can see, like what Karen was talking about, the Regner-Futzer maximum, that occurs at 20 kilometers, and you can clearly see that in MIT's data. So you know that their data is pretty solid as well. And also the green curve that you see here, that's actually a curve from the coincident detector mode. And what that is you have two detectors that are sitting on top of each other and they're connected. And essentially what that does is any false detection. So if one detects an event, but one doesn't, it will throw that out and it will only record the events that occur simultaneously on both detectors at the same time. And this is really important because if you look at the data here at 20,000 meters, that's a difference of 80% right there between 50 and 10 counts per second. That is a very large difference, and that's why we think for the ground-based experiments that's why there was such a large disparity at 24 and 55 meters. So in hindsight, we do think it would be very helpful. So in conclusion, the data that we got, although it didn't work as well as we thought it would do up until the altitude that we wanted to get to. The data that we did get was perfectly fine. It matched the relations, the model as expected. The results also suggest that, you know, using an HAB and this particular kind of muon detector from MIT, the Cosmic Watch detector, is absolutely viable for cosmic ray research, even if it's just for undergrad research or anything beyond that. And again, using the coincident detector would be a massive help in eliminating the false detection. So these are my references, and then there's some additional photos and videos here. I don't know how well this is going to work. This is just a 45-second clip. Yeah, so that's at the launch site right there. Actually, just to check, everyone can see this, correct? Yeah, okay. So that's it during its ascent. That is actually right after the balloon popped, which is another thing. When it popped, it started to wrap around the tether, which is why it's spinning so vigorously. You will expect a spin, obviously, but not that fast. But yeah, that's about it. So I'll stop sharing here, and if anyone has any questions.
Any questions for Jordan? Well, I'll ask you one, Jordan. Did the detector work after its landing? Did it survive the trip?
It did, yes. So when we recovered it, it was still quite warm inside. So at first we thought, oh, that's probably good. But again, in hindsight, probably not a good thing that it was that warm. But no, we tested it afterwards and it worked perfectly. We just think it was the heat that got to it at around 7,000 meters.
You're monitoring the temperature. Had you thought of connecting it through your Arduino to have a switch so that when it got, say, above 30 degrees, it would cut the heater off, and then if it got below 20, it would switch it back on again?
We actually didn't think about that, but that is a good suggestion, yes, because I think that would be the best way to do it, because just putting it on one setting would probably not cut it, I don't think, because it would either be too low or too high. So definitely, yeah.
Yes, it's something I might actually, if I find some time, pick up, because, you know, last summer we were practically up to 40 degrees at ground level in August. Be interesting to know whether that's a hard limit, or where it cuts off, or whether it's just sort of gracefully tails away. A little bit of work. Interesting. Thank you.
Yeah.
Any more questions?
Only one comment, really. If students next year are going to pick this up and repeat the experiment with what you have learned this time round, it might be useful to measure the barometric pressure as well and look at the correlation.
Definitely, yeah. Because before we realized that the detector was getting too hot, we originally hypothesized that the reason it turned off was pressure related or humidity related. And it would have been nice to have that data to look at and say, wait a second, that doesn't make sense for that to affect the detector at all, really.
Just one more. On the balloon, when does it when and how does it disengage? At what height? I missed that on your notes.
Ours popped at 25 kilometers. So it depends on what type of balloon you use. Some of them can go up to 100 kilometers, but those are very pricey. But yeah, as it rises, the gas inside expands, and then once it gets to that threshold, the balloon just pops, and then the parachute takes over, and it just gently glides back down.
You were very lucky it didn't go in the water.
Yes, yeah. For a moment, we thought it did go in the water because the tracker for a few minutes just refused to work. But yeah, luckily it didn't.
As I don't know whether you can see the comments feed and the chat feed, Jordan. There's a nice one from Karen. Great work, thanks. We've had thermal issues with our balloon ionization detectors, with them getting too hot. It's not the problem.
Yeah, it's a very strange situation, because again, you would usually think, oh, it's going to get too cold. But yeah, we didn't even realize that was the problem until we really looked at the temperature data, and then it just finally hit us like a brick wall. Oh wait, 40 degrees, that's not good.
A quick comment from me. I'm pleased that your equipment came to land on the north side of Morecambe Bay, because it's very sticky around the shorelines when the tide is out.
Yes, yeah. Sorry, what was that?
I don't think you'd have ever seen it again.
Yeah, no. Luckily, it landed in I think it was a farm. But the worst thing that happened during recovery was we were barked at by a couple of dogs. And
I don't know if you're aware, there is a high altitude balloon group using Raspberry Pis and tracking facilities. And we had one of their young members give a talk to a Raspberry Pi forum many years ago. Just a comment.
Yeah, I think when I was doing my research for it, I think I came across several just like amateur Facebook groups. I think there was specifically one in California, I believe, that were just doing their own sort of experiments with that. That I found very neat. And I think they used Raspberry Pis rather than Arduinos, I believe.
If you don't need the whole facility of a Raspberry Pi as a computer, then the Python is, the Pico offers weight advantages if you just need a simple controller.
Yeah.
Anyway, I'll try and contact you later on, Jordan.
Yeah, definitely. Actually, I'll go ahead and put my email in the chat if that helps.
Incidentally, I was a student of the predecessors to the University of Central Lancashire in those days, 50 years plus, it was known as Harris College.
Yeah, what the old building, I think it's still there, the Harris building, but I think it's now a law school, I think.
Well, I left Lancashire in excess of 35 years ago. Anyway, thank you for your presentation.
Okay, we've got some comments coming in the chat, and I must admit that's a cracker. The comment about making sure you've got good timing, because if you happen to be up there when there was a gamma ray burst, you'd want to observe it. And bearing in mind, last year, year before, we actually had one that produced effects that were visible, very much visible to the amateur community. Timing is everything. And good luck.
Yeah, I think I don't know if that sort of detector is capable of recording data for a gamma ray burst. I don't know if that would just fry it or something. It might. I don't know. Maybe. Yeah.
Okay, well, I think that's probably it. And unless anybody's going to pipe up, thank you very much, everybody. Thank you very much, Jordan. And when you're doing nuclear physics in Edinburgh, if you feel you have anything interesting to contribute, you would be very, very welcome to come and talk to us again.
Well, thank you for having me. It's a pleasure.
Okay, and as I said at the beginning, the next session will be in September. So I look forward to seeing and hearing from everybody then. Thank you very much and good night.
Night, everybody.
Good night.
Good night.
Good night.